let's make a quick review where we are. We have been talking about forces acting on a particle. So far, the assumption is that all forces act at a single point. We call that a particle. So all of them can be replaced with a single force being their resultant. Okay? We saw how to find the resultant. We learned how to write vector equation for each force, find the resultant, and we also have seen when you have all those forces, or the particle being in equilibrium, all those forces, some of the components would be zero. This was a definition of particle equilibrium in 2D, and of course in 3D you have also summation of forces along Z being zero. So this is what we've done so far. Assuming we have only a particle acted upon by forces, we know how to write the vector equation for each force. We know how to find the resultant by having the vector equation for each force. And if the particle is in equilibrium, we know some of the components of this resultant along every direction is zero. We did some problems in 2D. We've already done a problem in 2D. We want to look at the particle equilibrium in 3D. Okay, so I'm going to demonstrate that through an example problem. So I'm going to use a good problem from the book, which is actually a very good problem because it's very comprehensive and would demonstrate everything that you need to know. I can show you. So what we want to do here, we want to introduce the 3D equilibrium of a particle. That's what we want to discuss and demonstrate today. 3D equilibrium of a particle. This is a typical example. Okay? Let's say you have a weight that is supported by a cable that is attached to this weight. This weight weighs 200 pounds. So this is X, this is Y, and this is Z-axis. And this weight is also supported by cables that connect this to these points along these axes, or somewhere on those walls. Point D, point E, point B, and point C. Okay, so let's first write the position, the coordinate of these points. Okay, point D is obviously along x-axis, 80 inches from Y. Point E is on z-axis. This distance is 45 inches. Point B is 17.5 inches from Y, and point C is 25. I'm exaggerating these distances a little bit. And this is point A. Okay. The problem statement states that here is a pulley, and cable BAC is a continuous cable that goes around this pulley. So when you have a cable that goes around a pulley, you remember from physics, or you've had actually some problems in the homework set that you already submitted. If you have a pulley frictionless and you have a cable that goes around it, regardless of the orientation of this cable, doesn't matter. The forces on the two sides are always equal, right? And that's the case we have here. Problem states that this cable is a continuous cable going around the pulley that is attached at point A. Therefore, forces in this cable and this cable would be the same. That's what the problem states. But these two cables, this cable and this cable, are tied to this point, so their forces are different. They're not equal. So, in other words, you have three unknowns here. Force in these two cables, this one and this one. In 3D problems, I have emphasized this is the approach, step-by-step approach, okay? Step one, what was the step one? Anybody?
Right coordinates.
Write the coordinates. So you got yourself 2 points toward your exam one. Send me an email. That's how I do it at times. Give you bonus points if you answer questions. So encourage participation. Okay? But you sent me an email today. That's the promise. So step one, set up or show all coordinates of all points, important points. That helps you not to make mistakes, and also is a methodical approach that helps you to basically make the problem easier, okay? These are the x-axis, so the only dimension it has is 80, 0, 0. E is on the negative side of the z-axis, so coordinates of z are negative 45, they would be 0, 0, negative 45, 0, 0, negative 45. Point B is on the negative side of the x-axis, so would be a negative 17.5, 0, 0. Point C along the z-axis, so it would be 0, 0, 25. And point A is along the negative direction of y-axis, and this is given, actually I did not write that down, it is given as 60 inches. So it would be 0, negative 60, and 0. So that's the step one, easy. Easy, yet helps you to save time, because each time you're writing an equation, you don't have to start from scratch to figure out, okay, what is the coordinate here? That's all, okay? So once you've done that, step number 2, okay, write the vector equation for each force that you have. But this step involves several sub-steps. Let's say I call them 2.1. Step number 1 is, which is very important, although at this stage it may not seem to be, or you may not fully understand or appreciate that, but that's really the foundation of statics. And that is, draw the free body diagram of the particle. Since we don't have an object yet, we're dealing with particles. What does that mean? Identify this particle, which is point A, and show all the forces that are acting on that particle, okay? You have a force of 200 pounds downward, right? Then you have the force of A, D, force of the cable A, E, force in the cable AB, and force in the cable AC. And these two forces, we know the magnitude are equal. So this is the free body diagram of the particle. Once you've done that, then step or sub-step number 2 is you would write equation for all unit vectors, meaning that unit vectors that are along the direction of each force and define the direction of those forces. How many forces you have? 1, 2, 3, 4, 5. So you need to write all 4 unit vectors. For 200-pound force, which let's call this W. W is the easiest one because the unit vector is along the negative direction of Y. So U along W, right, is just negative J. And we know that the force is written as the magnitude of the force times its unit vector. So this would be the equation for that given load. Any question? Okay. Let's do F of AD. What is the unit vector along AD? Remember, tip minus tail. So here it would be 80 minus 0, 80I, 0 minus negative 60, so it would be plus 60J, 0 minus 0, 0. So 80 squared plus 60 squared, square root of that, okay? So F of AD then would be the magnitude of F AD that we do not have, times this unit vector, and I have simplified that. I have the answer here. After you simplify that, you get 0.8 I plus 0.6 J. So this is the equation for that force. Okay. You do the same for the rest. For F of AE, you need the unit vector of AE. Okay? AE, tip minus tail. 0 minus 0, 0. 0 minus negative 60, so it would be 60J. Negative 45 minus 0, so it would be negative 45K divided by 60 squared plus 45 squared, square root. So that will give you F of AE, and that simplifies to F of AE times 0.8J minus 0.6K. Okay. Next one, AB, F of AB. So you need unit vector of AB, which is B minus A. Negative 17.5 minus 0, I. 0 minus negative 60, so plus 60J, and 0 minus 0K. So 17.5 squared plus 60 squared, square root of that will give you F of AB. Okay, would be F of AB times negative 0.28 I plus 0.96 J. Okay. And the last one, F of AC. You have U of AC is C minus A. 0 minus 0, 0, 0 minus 60, so 60J. 25 minus 0, so plus 25K. divided by 60 squared plus 25 squared, square root of that. That will give you f of AC is magnitude of AC times 0.92 J plus 0.38 K. So you have the equations for all forces. That's, you've completed the step 2. Okay, any questions? Yes?
So on W, how, is that, so it's not a mass, it's like a
It's a weight,
So-
right? Yes.
So you'll never have to like multiply it by.
It's in, if it was a metric system, you're usually given that as, in terms of its mass, say 200 kilogram. But this is a pound force.
Okay.
That's the beauty of the English unit, which does not make any sense. Okay? So you have somehow the gravitational acceleration hidden in that. It's given as the weight, okay, so instead of the mass. Any other question? Okay. So now, the next step, you just simply apply equations of equilibrium. That means summation of all x components 0, summation of all y components are 0, summation of z components are 0. That'll give you 3 equations and 3 unknowns. So let's look at these. X component, this one doesn't have an x component, this one does, this one doesn't, and this one does, right? So you have, okay, yeah, 0.8, okay, 0.8 f of AD, right, plus negative 0.28 f of AB is equal to 0. That's the first equation, okay? Second equation is sum of the y components equal to 0. That means components of j. So this one has j component, this one has j component, this one does, and this one does, all of them, okay? So you write all of those, and you end up with, okay, if you write them all, you end up with negative 200 okay, plus 0.6 f of AD plus 0.8 f AE plus 0.96 f AB plus 0.92 f of AC, but since AB and AC are equal.
Here are some matches for Buck. Buck, the love Buck, A Bug's Life, the Buck, Life and Times of the People's Car, Monster.
That's the beauty of Siri, right? I never asked for it, right? Amazing. This is the goof up with the new iPhone operating system. Automatic turns on. So talking about bugs or something? Okay, so that's the equation for these two because f of AC and AB are equal. So I substituted for that here. And for K component, this one doesn't have one, this one doesn't have one. Yeah, here and here. So you will have negative 0.6 f AE, okay, plus 0.38 f of AC is equal to 0.
Go ahead.
This is amazing. Huh, somebody should write something to Mr. Tim Cook. I've heard so many complaints about this operating system, so now we are the witness. Okay. So these are three questions, three unknowns. You can solve these any which way you want. For instance, here you find FAD in terms of FAB, right? Here you find FAE in terms of FAB. Substitute in this one, doesn't matter how you do it. Even if you have an equation solver and your calculator, fine with me, as long as you write all these equations first. I've seen it, believe it or not, that a student just simply write summation of x is equal to 0, y equal to 0, z equal to 0, and they just simply write the answers. That's not acceptable. You have to show, demonstrate that you know what you're doing. But anyway, once you've done that, you get this would be the answer. If you solve these, you get force in AB comes out to be 77.1 pounds. Force in AE comes out to be 0.63 times 77.1, and force in AD comes out to be 0.35 times 77.1, whatever that is. I did not do the multiplication, I should have done it. So let's see, that would be, okay, this would be about 27 pounds. And this is 48.6. Okay? Easy, right? Very simple. Just remember the process. Set up the free body diagram by first, of course, writing these coordinates so you can keep track of those directions. Then you set up the vector equations for all the unit vectors. That will give you the vector equation for all the forces. And then just add up the x, y, z component, equate them to 0. That is the equations of equilibrium. Find the unknowns. Could not be easier, right? I promise you, study gets easier and easier as we go further and further. Yes?
Could you explain to me again why C and B are the same? It's just because
It's, the problem statement says that this is a continuous cable going around a pulley. So in other words, you have something like this. You have a cable going around a frictionless pulley, so the forces on the two sides have to be equal.
you could still solve it if that wasn't the case, though. It's
No.
messier.
But no, because if that was not the case, you have more unknowns than you have the equations.
Okay.
So you cannot have more than 3 unknowns.
Okay.
And if that would be the case, we call that a statically indeterminate. We'll see that later. Means that you cannot solve the problem with only the static equilibrium equations. Yes?
When there's like 2 pulleys, doesn't it change something? It makes it like half.
No, you're talking about pulleys and pulleys mechanisms. You're probably talking about something like this, right? Always consider a pulley as being something like a particle. So is that what you're saying? For instance, you have a pulley like here, right? Maybe another pulley here. Is that what you're talking about?
Yeah.
Something like that. Still the same, because if, let's say this is T, right? This would be T, right? So if this is T, this would be T, right? If this is T, this would be T. So as long as these are frictionless, that cable force would be the same throughout. Yes?
But wouldn't the total force be decreased by like a factor of 3?
No? What is the total force? Here you mean?
At the end.
Yeah, this is the force. Let's say you apply a force of 200 pounds here, right? So if this is a pulley, so the force here, if you cut it, if you cut this, that is 200, right? So if you cut this, this is 200, and this is also 200. So this has to be also 200, no. We'll get to these pulley problems. Yes?
when you add, like an added pulley, doesn't it make it easier to lift heavy weight? For every pulley that you add, it decreases. I think that's what they're referring to, decreases. the
Good
factor
question.
that has to pull
Well,
down.
what you're talking about is actually the moment. We're gonna talk about that.
Okay.
Yes, that is true in case of an object, and we'll get to that, yes. So any other questions? Okay, so equilibrium, 3D particle equilibrium then is easy, right? Now, let's see where we are heading. So you sure no more questions? Okay. So. Now let's again go back to forces. Yes,
The exam on Friday, what's?
up to here.
Up to here.
Right, no more, no more. And make sure to attend the help session, it would be very helpful. And I'll send you some sample problem and solutions as well. Well, let's see where we are. So far, we have made a huge assumption, and that is all forces act at a single particle, or they are all basically coinciding at a single point. So if you have that, if this is a particle, and I have several forces, you know, basically acting on this particle, this force, this force, this force, this particle will move in what direction? The direction of the resultant of these forces, okay? So if you have a particle, several forces acting on this particle, what you're dealing with is only basically a single force. And what that single force does, which is a resultant of all these forces, can move the particle along the direction that the force is acting. In reality, in statics or reality in structural analysis, we're not dealing with particles, we're dealing with objects. So forces are not acting on a single particle, okay? But they're acting on an object. In case of the fact that the force acts on a particle, right? This force moves the particle in the direction that is applied. So forces acting on a particle have just a single function, and that is what we call translational effect. Translational effect meaning moving the particle along the direction the force is applied. However, what happens if you have an object, not a particle anymore? Any object in the world you consider, it is supported through some kind of a connection that attaches that object to something, right? This table is supported by those four legs. This podium is supported by this rod, by this column. So when you apply a force to this object now, at some point in the object, obviously the force has a tendency of moving the object in that direction, but at the same time, since this object is held in place through some kind of a connection, with respect to that point, this force does something else also. Rotates the object. That rotation, of course, depending on how that connection is, takes different forms. So when you're dealing with objects instead of particles, now you're dealing with objects, okay? Forces have both translational effect as well as rotational effect. We've described the translational effect of a force through what? Writing the vector equation. Translational effect can be fully described because that effect is basically means a force, a resultant, and it's fully described by its magnitude and direction. So how do you describe a rotation? Rotation, of course, depends on how the object is held in place. if the object is held in place in such a way that it can rotate about a single point, we want to find the moment of, or the rotational effect about that single point, okay? So a point, sometimes the object is supported not by at a single point, but say, for instance, an axis. If I push on this door, there's no way this door would rotate about a point, but can only rotate about this axis. So you can have rotation either about a point or about an axis. Either way, we want to know how you describe rotation. The rotational action of a force is described by a quantity which we call that moment. So moment is a quantity that describes the rotational action of a force. How? If you have an object, okay, and is acted upon by a force, and you want to find what is the rotational action, how do you describe that? In case of a force, we wrote it as a vector equation. Moment is also a vector, but what kind of a vector that is, and how do we write that vector equation for the moment? First, look at the rotational effect about a point. So let's say you have an object, it is connected at a single point somewhere. You apply a force to this object, so you have basically something like this, okay? Doesn't matter how that is. And you want to find out what is the rotation, and this is not necessarily parallel to any of these axes, okay? So you want to find out what is the rotational effect of this force about this point of rotation, x, y, z. This is how we describe or derive that relationship. We consider a vector that is connecting this point of rotation to any point along this force. This is called point of rotation, and we call this position vector. It is a vector that describes the position of that force about the point of rotation. Moment of this force about a point, which we write it this way, is a vector that is found by setting up a determinant whose first row are the unit vectors of the coordinates. Obviously, a force can be written in vector form, right? We know how by now. Any force can be written as a vector like that, and including this position vector can be also written, as long as we have all the information about the coordinates of these 2 points, can be written like this, okay? So the moment can be fully described by expanding a determinant whose first row consists of I, J, K. The second row are the components of the position vector, and the third row are the components of the applied force. So this is R, this is F. Remember, I've seen this mistake made over and over again, that the students set up this determinant and they write for the second row component of the force and the third row being component of the position vector. That is completely wrong. Don't make that mistake. This is the definition. This is the way you set up. So if you expand this determinant, and you've seen how to expand the determinant from somewhere, calculus, you can expand a determinant in terms of any row or column. So if you want to expand it about any row, like this first row, each row each element of the row has a sign that alternate. For instance, this is positive, this is negative, this is positive. To expand it according to this row, you eliminate the column and the row corresponding to the first element. You end up with a 2 by 2 determinant, and the value of this 2 by 2 determinant is product of the upper left hand element multiplied by the lower right hand element minus the product of these two. In other words, this is expanded as Ry Fz minus Rz Fy times I. You do the same for J, except that this is now negative. So it would be negative, you eliminate the column and the row corresponding to that, and this would be the determinant left. So it would be Rxfz minus Rzfx J. And then the third one. So you eliminate, again, the column and the row corresponding to that, that is positive. So it would be positive times Rxfy minus Ryfx times K. This is the equation for that moment about point O. In other words, this is the x component of that moment vector. This is the y component of that moment vector. And this is the z component of the moment vector. So being a vector, obviously, the magnitude of this vector would be what? Mx squared plus my squared plus mz squared. What is the direction? Obviously, the direction is fully described by that vector equation. But if you just want to feel that, the direction of this vector is this. First of all, this vector is perpendicular to the plane made by these two vectors, r and f. You remember, moment is the cross product of these two vectors. And this is the value of that cross product in terms of as a vector. But you remember from the cross product, this is how we found the direction. If this is the first vector, this is the second vector, M is perpendicular to the plane of these two. Its direction is perpendicular to this plane, and in order to find the actual direction, you put your fingers along the first vector such that as your fingers tilt, this tilting can move this first vector towards the other one. So obviously, that's the only way you can do that, because if you put your fingers like this, when your fingers tilt, would move this away from that. So if that's the way, then your thumb shows the direction of that. You don't need to know that. It's confusing. You don't need that, because this vector equation is fully describing the direction anyway. Okay? Obviously, there's a special case, and that is when both the force and this point are in the same plane. In other words, this object is a 2D object. So both of these are in the same plane. Things get a lot easier. And in this case, we go by the direct definition of cross product. In other words, if you have, let's say, a force like this, and this point is here, so both of them are in the same plane xy, when you draw this vector r, we know from definition of cross product, the magnitude of m is the magnitude of r times magnitude of f times the sine of the angle between these two. This is definition of cross product, okay? From definition of the cross product. So if you look at it, if I draw a line from O perpendicular to the direction of F, so this vertical distance D, R sine theta in this triangle is nothing but that D. So M then can be written as simply F times D. Okay? So the magnitude of a 2D moment of force in a 2D plane is just the magnitude of the force times the vertical distance from the point of rotation to the direction of the force. So things get easier. Okay? So first let's demonstrate this general concept, and we go step by step. We're going to do problems to fully describe 2D case as well. Because in 2D case, since you quickly find the magnitude, and we know that the direction is always perpendicular to this plane, all you need to know is whether its rotation is taking place in the clockwise direction or the counterclockwise direction. That's it. Cannot be more than that. We'll see that. But let's focus on this problem first, this case first. So I'm going to do a quick problem 326 in the book to demonstrate this concept. Okay? 326. So let's say you have an object being a pipe or a rod or something like that, 6 meters long, along the x-axis. Tip of this object is connected by a cable to a point on this wall, and the distance from these two axes, obviously, which are the position of that point, are given. Okay. We know this cable is exerting a force of 25 kilonewton along to this pipe. In other words, the force of BC acting along this cable is given as 25 kilonewton. So this is what you have given. This is the problem given. What we want is to find a moment of that force BC about point O. So we just want to know how that force rotates that object about point O. Or in other words, find the moment of that force about point O. Okay? So this is a 3D problem again. So where is the first step? Write the coordinates. So this is just 6, 0, 0. C is on this quadrant, so has no x, 0. Its y is 2.4, z negative 4. Okay? And O obviously is 0, 0, 0. So that is step 1. Coordinates. Remember that. Step 2, you need to write the equation for those vectors. To find the moment of that force about point O, you write, so in other words, you set up your position vector as the second step. How do you set up the position vector? You need to connect this point of rotation to any point along F. Remember, engineers always take the easy way out. So do not make life more difficult than it is for yourself. So if I tell you find a position vector, I have two choices. Then you need to connect this to any point that you know its coordinate along this line. Obviously you have 2 points, this and this. I would consider this as the position vector. Why? It's easier. Because in this case, R can be simply written as 6I. If I choose, say, this one as R is okay, and would give me exactly the same result. But then you have two components for R. This one has only one component. Y and Z components are 0. So when you think of this determinant, these two are 0. Makes it easier. So always find the easy way. Okay? So now you need to write step 3 would be write the vector equation for the force. So you need to write again unit vector, right, times the magnitude. So 25 times the magnitude, 0 minus 6, minus 6I, 2.4 minus 0, plus 2.4, J, and minus 4 minus 0, minus 4K, divided by 36 plus 5.76 plus 16. Square root, you simplify that, and I believe I have that somewhere here, okay? Okay. No, I haven't, I don't have it, but anyway, it doesn't matter. So you find something like this, f of x, I, plus f of y, j, plus f of z, k. So this would be the equation. And then set up the last step, easy, right? You just simply write the vector equation for the moment, which is this determinant, fully described by this determinant. R is 6, 0, 0. F is fx, fy, fz. And if you expand this determinant, you will see that you have what? This would be 0, so no I component. If you expand in terms of j, you have a component, right? 6 times that. But for k, okay, also only 1. So you can just expand this and you'll have I, okay, for I you have, for I you have nothing, you have something for j, and something for k. I will do more problems next week. We'll focus on moments, moment about a point, moment about an axis, then we get to couples. So this is just an introduction.
How do you choose your R? Any
That doesn't matter. Just connect the point of rotation to any point along this line. Arbitrary. As long as you have the coordinates of that point. So the choices are either this or this, right?
Okay.
That's it.
Okay.